Thank you for giving me the opportunity to talk today, and I'm going to talk about some microanalysis in the minerals industry, some application using the JdLC Centre. It's going to be very much more metallurgical bent, probably, but certainly many of the metallurgical issues can be associated more with the microanalysis issues. So, of course, you probably all know, but sometimes people always tend to forget the mineralogy of the ore dictates the selection of the treatment route and what improvements can be made to a process. So even you get the geology, you've got to be able to tie it in with the metallurgy of the process. Of course, the benefits of automated mineralogy techniques I've listed there is to reduce circumvent risks associated with the variability of ores, characterization tools, debottlenecking in some of the metallurgical applications, and tracking the deportment of minerals in various process streams. It's particularly been used very much in metallurgical, probably more than some of the geological. And the tool we use a lot is the TIMA, or the test scan integrated mineral analyzer, which we'll mention a bit. And basically, you might be familiar with the MLA QuentScan. So the TIMA is essentially the similar type of machine. It does Modal mineralogy, mineral associations, size-by-size liberation analysis, digital text maps, which we'll also show, bright field searching for precious metals, and you can look at grain size, shape, and porosity. Now, the important thing is not just use of one technique, but in applications is to look at utilising integration of different techniques. So if you have an ore or concentrate or sample, preparation, in a preparation, as Will mentioned, we've got a self-rag or electrodynamic disintegration technique, which can liberate particles without ending up with lots of fines or breaking up, and keeps the integrity of the minerals, which tends to be lost when you crush it. Use standard sort of techniques of optical microscopy, X-ray diffraction, chemical for bulk analysis. Use the automated mineralogy techniques to characterize sort of for statistical purposes. Back some of that up with some chemical analysis using a laser ablation to get chemical analysis, and using the FIB-SEM with the in situ TOF-SIMS for high resolution detail. And of course, we can go to the next step if need be for the ultrafine analysis, which I won't go into detail here. Not normally applicable at early stages. So the application that I will just, we use a number of different things, but for lack of time I'll just go through one particular application we use, which is pretty much evident at the moment, is the battery minerals, in particular the malleability of lithium pegmatite ore bodies to processing for the extraction of lithium. We have at the moment a MERA project looking at the geology, mineralogy and metallurgy of EMET materials. It's, the aim of this is to develop a geometallurgical framework of WA lithium pegmatite deposits to improve basically the efficiency of exploration, mineral beneficiation and processing techniques. It's funded and state government funded, but also in industry funded by and with GL Survey, Lithium Australia, Rio Tinto and Galaxy Resources on board. So it's a three-tiered process, but I won't go into too much detail of this one at the moment because we're still working on it, but give you some examples. So in terms of the application in the lithium pegmatite ores, you probably already know the major source of lithium and lithium, cesium, tantalum pegmatites is the spodumene petalite, and also the lithium-bearing micas with various concentration. And it's important not only understand the mineralogy from maybe from a geology perspective, what's in there, but also from a processing point of view. The process involves a physical beneficiation step to liberate and concentrate the lithium-bearing minerals from the gangue. Elevated temperature and chemical processes normally done to leach and recover lithium, involving sort of calcination of spodumene at 1100 degrees and sulfate roasting at 250, and then water leaching. Mostly mining companies are chasing after the high-grade spodumene deposits, and some of the low-grade ones, including lithium micas, have yet to be developed. And there still seems to be a limited detailed knowledge of some of the mineralogy and deportment of lithium in many of these deposits, despite a lot of work done on pegmatites over the years. So the first thing one always does is obviously is to generate a calibration set of minerals in the database, which you analyse in detail, wet chemistry, laser ablation, X-ray diffraction to define the minerals, which you can use then as a base for database benchmarking, looking at different minerals and different deposits. At the moment, so we've been looking at field studies conducted on target samples which cover most of the different LCT pegmatites in Australia. But I'm just going to give a couple of examples of some of the work that we've published, one on Pilganora pegmatite and on the lepidolite hill. So just as an example. So like all bulk analysis, you need some chemical analysis of the samples, and this just sort of illustrates, in this particular case, the lithium grade is pretty similar despite being different ore bodies. The lepidolite is made up of mainly potassium, rubidium, cesium, fluorine, sodium contents, whereas the Pilganora sample is high in beryllium, calcium, magnesium, carbon, and a few other elements. So we can use Modal mineralogy with TIMA X-ray and then confirm with wet chemical analysis comparisons to get the mineralogy. So here's just looking on left-hand side is the Pilganora, which is mainly spodumene. Some of the lithium mica is present in there, the lepidolite, trilithinite, muscovite, beryl, and a lot of feldspar and albites, whereas the lepidolite hill is mainly made up of lepidolite, which is the lithium mica, and, made up of a number of different things. So important when looking at these things, so there's the morphology and textures. So different each of the ore can have different lithologies with different textures. For even spodumene, you can get spodumene as seen on the left hand side, clean grains, or you can get different degrees of alterations or intergrowths through the micas and calcites. And even the lepidolite, which is mainly just a lithium mica, can be quite complex in its structure, as seen on the right-hand side there. Fine textures, and we can use electron backscatter diffraction to sort of look at the texture in terms of the orientation, contrast, and show cleavage, random orientations, which can. And looking at increasing detail using the FIB-SEM-TOF-SIMS basically, because it's using standard energy dispersive analysis techniques, you can't pick up light elements like lithium. We can use the combination of the TIMA data and the TOF-SIMS on the FIB-SEM, which I added the two instruments in the same room to go from one to the other. We can look at the correlations of the different light elements to the other elements. And as you can see here, the top one is the spodumene, looking at lepidolite zones where the main lithium is obviously associated with the spodumene, but you get variations, and there you've got potassium, rubidium, cesium, fluorine, and manganese in the lepidolite grain disseminated with some lithium, and the lepidolite hill sample shows a strong correlation of lithium with the fluorine, cesium, rubidium, and the lithium pore, which is associated more with the muscovite, has high sodium associated. So we can look variability in compositions right down to a micron scale. The laser ablation, of course, we want chemical composition information. Not all spodumenes are not the same. They have obviously different textures in there and different alterations and everything, but also the compositions can vary. So lithium, aluminium silicate, but it can contain high concentrations of magnesium, calcium, manganese, iron. So, and you get white spodumene, you can get green one, which is associated with impurities. In addition, the mica compositions, the different mica polytypes can be classified based on the strong correlations of the lithium to aluminium silica ratio in there, and obviously lithium and fluorine, which is associated with a lot of the lithium micas, and so we can look at the correlations there. And so we can distinguish between the different lithium micas as well as the muscovite or the lithium pore muscovite, which has different structures. So overall, encompassing all the data, of course, you can come up with a lithium deportment and certainly the Pilganora sample contains mainly lithium in the spodumene and some in the lithium micas, where obviously the lepidolite one is mainly in the lithium micas and some a little bit in the tourmaline. One of the important things, of course, is what sort of grind size do you need to, from a beneficiation step. Using the TIMA, we can categorize we can do size by size fractioning and look at different polished mounts and measure the different liberation characteristics. So, for example, the top one there shows a low liberation. So essentially, it's just showing a histogram there of the screen size of the bottom, and on the right-hand side of it, we've classified in terms of liberated through to locked, depending on the surface area, how much of the particle is actually exposed and how much is encased and locked in another mineral. So the top example shows you one where obviously with spodumene, so looking at a number of numerous grains, we can look at the different, spodumene is obviously strongly associated with the calcite and lepidolite, and it's mostly in the middlings or not entirely liberated, whereas other samples we can look at, it's liberated because most of the spodumene is exposed with little contact, as in the bottom one there. And we can go further and do plot up grade recovery curves, which is very important in sort of in the beneficiation side of things, in terms of like flotation, to work out theoretical recovery curves, and then you'd back that up with your test work program. So that's from the other thing is from the process downstream, of course, in terms of the processing side of things, that spodumene in particular, in order to extract the lithium, has to be calcined to convert it from alpha, the monoclinic alpha structure, into a beta tetragonal structure, which actually expands and allows the lithium to be extracted. So one of the problems with a lot of is in the calcination is trying to get a nice homogeneous product which doesn't stick to the walls, doesn't have any clinter effects or sintering, which they associate. So we can use our in situ X-ray diffraction instrumentation. Here is just a plot of temperature versus the different X-ray diffraction patterns for two types of spodumene, a white spodumene and a green. The right-hand side is just pictures of showing how a fairly clean spodumene, whereas the bottom one is a green spodumene with some impurities. And long and short of it is that the thermal properties are influenced very much by the presence of these impurities. 1 minute, is it? Oh, shit. Okay. So the other thing, looking at the impurities, of course, in calcination, we end up, because you've got some extra minerals in there, they tend to degrade. The spodumene is calcined at 1100 degrees. Mica's melt at lower temperature, and feldspars melt at slightly higher, so you need to control the conditions so you don't try and reduce the amount of melt. So this particular picture shows on the left-hand side a white spodumene where all the lithium is nicely homogeneous in the things, whereas on the right-hand side where we have melts or other things, it's encapsulated over the spodumene, despite being beta spodumene, which we've now got a case. So in other words, you have to control some of your impurities in there. So inference is just about finished. Yes. So basic pegmatites have different lithology and different responses to metallurgical treatment options. Feldspars and micas limit the roasting temperature and reduce recovery. Calcite in there, some of the samples can consume acid. Fluorine, obviously, and if you're going to treating micas, can be an occupational health and safety. Some of the other elements that are dissolved in the process, higher and favourable resource covering of other things. So overall conclusion, digital image analysis microscopy techniques are coupled with the analytical mass spectrometry techniques. It's a very effective tool for quantifying and understanding mineralogy and identifying factors that can improve it. So encompassing all our facilities at John Delata Centre, we can get a pretty good picture of some of these things. Thank you.